Okay, here's the paper, and I'm gonna start the timer now. All right, let's go. So I'm gonna look at the question here. This is question 1. All right, gonna write in here then. Question 1. A light elastic string AB has natural length 4a and modulus of elasticity lambda. The NA is attached to the fixed point, and at the NB is attached to a particle of mass m. Okay, so NA is fixed here, and this is the particle. Particle is held in equilibrium with the string stretched by a horizontal force magnitude kmg. All right, the line of action of force lies in the vertical plane, the same vertical plane. Yeah. The string AB makes an angle alpha with the vertical, where tan alpha is 4/3. With the particle in this position, AB equals 5a. Yeah, everything is in the diagram already, guys. As shown in figure 1a, show that lambda is that. Okay, so lambda is the modulus of elasticity, and then we're gonna solve that by just use static equilibrium. So if I draw the force diagram, this is kmg here, and of course the mass of the particle is m, so there is a weight here, mg, and there is a tension, right? Tension of the string. And because we are given also this is the alpha, so if tan alpha is given to be 4/3, we can do a little, trick triangle here, right angle triangle, where tan would be 4/3, so got TOA there, just OA. And then of course we know that this should be 5 from Pythagoras. Well, that means, without any sweat, sine alpha, this is alpha here, sine alpha should be 4/5, and cos alpha should be 3/5. Just for later use, So we don't need to solve for alpha, So now we solve for equilibrium, For the x-axis, we have kmg equals t, so this is going to be also alpha. So it's going to be t sine alpha, right? And for the y-axis, we have mg, the downward force, equals the upward force being t cos alpha. Right, that's my alpha. Okay, so if we divide them, we see that we got the k, so everything will cancel. But now we want to solve for lambda. All right, so we can divide both equations first to get k. You can see that if I divide kmg by mg, I got k, and t will cancel as well. On the right hand side, you get tan alpha here. So that is basically saying that k is tan alpha, which is just 4/3 as well, right? And now if you plug k into the first equation, right? So we get 4/3 mg. Now t is the tension in the string, which is the same as lambda over natural length, where the natural length is given to be 4a, times the extension, right? Now the extension, we can find it by looking at the string directly, because the string is now stretched at 5a, so the extension is just 5a minus 4a, which is just a, Hope you guys okay with that. So that's the t part, which is this guy. Now we have the sine alpha as well. Don't forget, sine alpha is again 4/5, just here, So the a cancel there, and then we got lambda to be, also 4 also cancel here, so we have 20/3 mg, right? And that is as required. That's just part A done. Okay, part B. Find the value of k. Well, I think we got that already, didn't we? Somehow I got it before A. Okay, but I'm just gonna write the working again maybe. So kmg divided by mg equals, what was that again? T cos t sine alpha divided by t cos alpha, right? So k is just tan alpha equals 4/3. I don't know why there's so many marks on that one, but this is just static, guys. There's nothing much unless I made a mistake. So I'm just going to double check. So it's just tension And then, yeah, tension and tension. That should be fine. Okay. That's it. Next one, question 2. Part A. A thin hemispherical shell with center O and radius A is fixed with its open end uppermost and horizontal. Okay? Particle P of mass M moves in a horizontal circle. Okay, we see that. On the smooth inner surface of the shell, the vertical distance of P below the level of O is D. Okay, we can see from the figure. Find in terms of M, G, D, and A the magnitude of the force exerted on P by the inner surface. Wait just 1 second. I just heard something, guys. Give me 1 sec. Actually, it's nothing. Don't worry. I'm okay. Yeah, so if we just draw our diagram a little bit, right? It's just a circular motion on the horizontal plane. And we have here the particle. Now, because the center of the hemisphere is here, so that means the normal, right, should be acted towards the center. That's R. All right? And how do we know the angle? Well, this is the angle to the upward vertical, maybe. So let's call that theta, right? Okay. And then we can do a force diagram. So this is mg. Yeah. And then, hang on. The radius of the rim there is A. D is just below that. So this is distance D, right? Okay. Okay. So yeah, let's draw a, like a little right angle triangle. So this is also O. This is also R, right? We know that the radius of the sphere is not R, is A. That is also A, right? So we know this distance. And then this is the D. Okay. So we know that to find this angle here, if we want, that is going to be, well, we know that this is going to give us what? Sine theta equals D over A, right? Yeah? So sine theta equals D over A. That means if we want anything to do with this angle, we can just do, 90 minus that angle, right? Just in case, yeah? So we keep that. So sine theta equals D over A, okay? And now, and this is not theta anymore. This is the opposite to theta. So this is 90 minus theta, right? So if we do force, yeah, F vertical, all right, because the vertical direction should be in equilibrium because it doesn't move up or down. So it's just moving in a circular motion. So we're going to resolve the vertical forces first. That means R cos 90 minus theta is going to be equal to mg. Well, cos 90 minus theta is just sine theta, right? Yeah, it's just because we have sine theta already. It's D over A. So this is R sine theta, which is D over A, right? Okay, equals mg. Yeah. Yeah, is that done? So we cut everything, right? And is that done? Yeah, the R here will make the circular centripetal force. So R is just mga over D, right? So mgad, that's it. I'm done with that, actually. Okay. Part B. The particle moves with a constant speed v. All right, now this is where we need to resolve towards the center now, to the left, right? So remember we got R cos 90 minus theta to be the upward component. So if you resolve to the horizontal component, that would just be R cos 90 minus theta, which is actually, r sine 90 minus theta, which is the opposite to, so earlier we got sine theta here, right? Which we use this. So we're just going to use cos instead, right? So r cos theta will be equal to the centripetal force, which is mv squared over, well, we got to be careful about the radius, right? So the radius here, yeah, it's going to be this guy, right? And that is a cos alpha, right? So if you resolve a down here, you're going to get the radius, which is a cos theta. Okay, so I'm just going to write a cos theta here, and that's it, yeah? So we got r, and then a cos squared theta equals mv squared. We want to find v in terms of g, a, and d. So v is just square root of ra cos squared theta divided by m. Now we got earlier that the r is just mga over d, right? So we're going to use that. Mga over d times a cos squared alpha over m. So m cancel, right? And then there are a and cos theta that we can bring out, right? And in square root, there will just be g and d. So we write a cos theta outside the square root, and then g over d inside the square root, yeah? And cos theta will just be what? Well, if sine theta is d over a, what would be cos then? Well, we can find cos by just doing cos theta equals square root 1 minus sine squared, right? So that's d squared over a squared, or it would just be a squared minus d squared over a squared, yeah? Yeah, so that would be the cos theta. Okay, so I think I shouldn't have brought cos outside, so I'm just going to keep a outside and cos squared kept inside maybe, yeah, which is that thing right there, here, because it's already in the square root. So here I wrote cos squared theta is just a squared minus d squared over a squared, right? A squared minus d squared over a squared. That's complicated, but then we can simplify, can we not? Because if you bring a out here, yeah, a is the denominator there, a squared, it's going to cancel. And here inside we have g over d times a squared minus d squared. So a cancel, we just get square root of g over d, and then a squared minus d squared. There you go. That would be my answer there. Okay, a little complicated, but yeah, I guess that's math. Okay, number 3. Particle P is moving along the x-axis at time t seconds, where t is greater than or equal to 0. The displacement of P from the origin is x meters, and P is moving with velocity v in the positive x direction. The acceleration of P is stepped in the positive x direction. When t equals 0, x equals 15, and v equals 8. Show that v equals that. All right. So this is, calculus on the kinematics. So we know that v equals dx by dt, right? Yeah, we know that. But we want v in terms of x. Okay. Oh, well, we should use this. We should use the other one. So a over v equals, a is dv by dt, right? And v is itself dx by dt. So the dt cancel, and the more familiar formula for you would, the more recognizable one would be that. Yeah, when you study at school, they will have told you that. But it comes from this, yeah. So we're gonna plug acceleration as that, yeah, 3 root x plus 1 over 4, v as v, and then we're gonna integrate both sides, right? So I'm gonna put a as 3 over 4 square root x plus 1. Well, that is just x plus 1 to the power of half, right? And I'm gonna move v up here, v dv, and x dx up here, yeah? So that's just to get ready for the integration, and now we integrate. Okay, so, and then we're going to make v the subject. Okay, so we integrate that, we get 3 over 4. Wait, hang on. Let's apply the bounds as well. So, yeah, the way I would do this is to apply the bounds when I integrate. So, x at t equals 0 is 15, right? So I put 15 here. And v is 8, so I put 8 here, yeah? That's the initial conditions. When t equals 0, x is 15, and v is 8, all in the positive directions. And then we want to solve this for the particular solution where we don't have any constant after the integration, right? So we're going to put this as a v and this as an x. And there is no hassle needed to find the integration, the constant after integration. When you substitute the bounds x and v on both sides like that, you're going to get that equation. Okay, let's try. So I'm going to put 3 over 4 outside, and then I'm going to integrate that already. Well, this requires some P3 knowledge, guys. That's going to be x plus 1 to the power of power added by 1. So we're going to get 3 over 2 divided by 3 over 2. So I get 2 over 3 here, yeah. And then reverse chain rule, well, we divide by 1, so that doesn't quite matter here. So that's fine. And then we're going to sub 15 and x for the upper and lower limit. And on this side, we have v squared over 2, yeah, and then sub the bounds v and 8. So that's it. Now, what do we have here, yeah? If I bring 2 over 3 outside, right, it's going to cancel, right? So it's going to be 2 here and 3 here, so that's 1/2. And then sub in here, we get, subbing x in, we get that. Subbing 15 in, so that should be minus. Subbing 15 in, we get 16 in the brackets. 16 to the power of 1/2 first, we get 4, and then 4 to the power of 3 is 64, right? On the other side, we have v squared over 2 minus 8 squared is 64. 64 divided by 2 is just 32. Yeah, that's it. So if we expand on either side, right, this is going to be 1/2, and that's going to be minus 32, and that will cancel, right? So the minus 32 will cancel, and the 2, the dividing by 2 will also cancel. We will be left with x plus 1 to the power of 3 over 2 equals v squared. And that means if we square root both sides, or power by 1/2 on both sides, we're going to get v equals x plus 1 to the power of 3 over 4 as required. We power by 1 over 2 both sides. I hope you can see that, yeah? Okay, so that's A done. Part B, find t in terms of v. Well, yeah. So let's see, v in terms of t in terms of v. Okay, so v equals dx by dt, right? And we already got v there. Yeah, so we're just gonna sub in that expression of v into this. So I get x plus 1 to the power of 3 over 4 equals dx by dt. So it's just separation of variable all over the places. I mean, if you are good at P4, then this should be fine. So then we have what? I mean, I'm going to just move dt here, and I have a 1 there. I mean, just, yeah. And if you move this down, it's going to be a power of a negative. So I'm just going to write x plus 1 to the power of minus 3 over 4 dx here. And then we're going to integrate both sides, right? Yeah. So I have t here. Oh, again, let's apply the bounds already. So t0, right? X is at, again, 15. Now when t equals t, x will be equals to x. Yeah, that's when you apply the bounds. It's going to make life easier, trust me. So that's going to be just t minus 0 when you sub in the bounds and everything, right? Yeah, I'm just writing so that you see. And then for that one, if we integrate first, we're going to have, so that is just x plus 1 to the power of power added by 1. So that's going to be added by 4 over 4. That's going to be 1 over 4. And then divided by 1 over 4. So you get 4 here. And then the bounds would be 15 and x, right? So the left-hand side is just t already here. And then that would just be 4. What is that? X, yeah, still x plus 1 to the power of a quarter. minus, again, 15 plus 1 is 16. 16 to the power of a quarter is just 2, isn't it? Yeah, I believe so. Square root you get 4 and square root again you get 2, yeah. Yeah? So that is just t equals 4 and x plus 1 to the power of a quarter minus 8. Right? Oh, hang on guys. I thought they asked t in terms of x. Alright, I did it all wrong. Okay, sorry about this. I gotta do everything again. Okay, t in terms of v, sorry, v, not x. Hang on, so we have a equals dv by dt, right? Yeah, I guess. And for a itself, it's, hang on, let me write this equation again. A over v equals dv by dx, right? And then t in terms of v. We know v in terms of x, but we want t in terms of v. Okay. So v equals dx by dt. Again, I should have kept that. Okay, let me just keep everything that I did here. Sorry about this. Okay. Actually, this is not a waste. Sorry. Because we know that v is x plus 1 over x. Sorry, v is x plus 1 all to the power of 3 over 4. So that means if we cube root on either side, we get v to the power of a third equals x plus, wait, hang on. Yeah, that's right. X plus 1 to the power of 1 over 4, right? Yeah? And then we can sub that back into the t equation. So t is actually equal to 4. And then v to the third minus 8. Yeah, that was it. I just didn't see that. Sorry. Okay? So I think that was it, isn't it? Let me just double check. So you put a third here. Yeah, I think this is it, guys. That's for me. Next one, question 4. We're at 20 minutes now. We should be okay, I hope. There you go. Part A. In a harbor, the water rises and falls with the tides and simple harmonic motion. On a particular day, the depths of water in the harbor at low and high tide are 4 meters and 10 meters respectively. So we have high tide here being 10 and low tide being 4. Right, so that's some kind of ground maybe, yeah? Okay. Low tides occur at 12 o'clock and high tide occurs at 18:20. Okay, so there's a difference there. Part A, find in meters per hour, yeah, the speed at which the water level is rising on this particular day. Okay, at 13:35, right, that's 6 marks there. So we probably need to get the simple harmonic equation first, the formula. Right, so clearly the amplitude, or x0 here, well, let's find the equilibrium position first. So the equilibrium position is just 10 plus 4 divided by 2. So the equilibrium is just in the middle, yeah? 7 meters. So this is when x equals 0. You got to be careful. X equals 0 at equilibrium. But that equilibrium might be above something. Yeah, in this case, it's 7 meters above the ground. Yeah. And then we know that we already got the amplitude here. So x0, which is the amplitude, is just 3 meters. Right? And then, yeah, we also know the time, right? Because from low tide to high tide, I'm guessing that's going to be half period. So when you go from this up to this, yeah? Okay? Yep. So t over 2, which is half the period, is in hours. It's going to be 6 hours and 20 minutes. That's half the period. So 6 hours and 20 minutes is just 6 1/3 hours, right? So t over 2 is just 6 and 1, 6 point, it's not 6.5, but it's 6 and 1 over 3. So that's 19 over 3, yeah, hours, yeah, just so you know. So t is just 38 over 3 hours, yeah, just writing units as well here. Well, if we form the simple harmonic equation, let's say we start at here. Well, actually I prefer to start here, but hang on. So okay, so if from the low tide going to the equilibrium, so low tide going to high tide is 6 hours 20 minutes. That means low tide to equilibrium is going to reach this level at the first time at so time of, it's just 12 o'clock plus 3 hours and 10 minutes, right? So that's going to be 15:10 hours. Yeah, that's going to be in 15:10 hours. So the 13:35 hours here is actually below the equilibrium. All right, so it's probably somewhere here. Yeah, we want to find at this location what is the speed. Okay, now we know the equation, right? That if you know the location, we can find the equation of we know the formula of speed as what is it? Is it omega? I actually forgot the formula. I need to look. Is there a formula here? No, I probably need to recall. Okay, so let me just try recall. Yeah, I think it's just omega square root amplitude squared minus displacement squared. All right, yeah, that's the formula there. Okay, so omega is just 2 pi over t. So omega is just 2 pi over t. And t we know already, we're going to keep the same unit as per hour here. So t is in hours. So that's 2 pi over 38 over 3. So that's going to be 3 pi over 19. Yeah, because 2 over 38, we can cancel that. Okay, so that's the omega there. And we already know the amplitude being 3 meters. Now the only thing we don't know here is the displacement. So where is that location, right? We are given the time, so we're going to use that. So this is actually the work that comes later, right? So we need to find the time first. Sorry, the displacement. All right. We are going to use, say, because we start at an n here, so we're going to use we should use the cos, right? So x equals x naught cos omega t. Yeah, where t is in hours, of course. All right, so let's do a sanity check here. When t equals 0, which is at 12 o'clock, yeah, that's where we start. We're gonna start at the bottom, right? We're gonna start at the bottom. So when t equals 0, this whole thing will be 1. So x naught is this distance here, which is 3 meters. So I should put a negative here, right? Yeah. So this is positive x, this is negative x, right? Okay, so that's fine. So minus 3 cos, again, omega we already got to be 3 pi over 19, yeah? And the time, right? The time in hours here from 12 o'clock there. So 13:35 is 1 hour and 35 minutes. So 1 hour and 35 minutes, like that. So that is just what? 95 over 60. If I simplify that, I get 19 over 12, right? Just using 5 to cancel that. So this is 19 over 12. I expect a negative number here because it's just below the equilibrium position. So that would just be the x value, yeah? So what is that? That's just minus 3 3 pi over 12, that's pi over 4. Cos pi over 4 is just cos 45 degrees, so that is 1 over root 2. So this is minus 3 over root 2, which is just minus 3 over root 2 below the equilibrium. But we're going to use that anyway. So if we square this and plug in this, yeah, it's going to be, what is that? 9 over 2, isn't it? Yeah. Okay, so I'm just going to shrink that. Okay, so this will be equal to 3 pi over 19. That is 9 minus 9 over 2, so is also 9 over 2. 9 over 2 square root will be 3 over root 2, right? And we're gonna find that in, yeah, probably some decimal places. Okay, so that's gonna be fine. Yeah, okay. So fraction 3 times pi times 3 and then over 19 times root 2. Here we go. We can keep everything exact like that. Also, we can find the decimal of that. I'm just going to do 3 significant figures, so that's meters per hour, right? Because our time unit is in hours. So that's part A. Phew. Okay, part B. Find the earliest time after 12 o'clock on this particular day at which it is safe for the ship to enter the harbor, giving your answer to the nearest minute. A ship can only safely enter the harbor when the depth of water is at least 8.5. So if we look at our diagram again, 8.5 is around here, yeah? A little above the equilibrium position, 1.5 above the equilibrium position, okay? The earliest time after 12 o'clock, so the water will rise from here up to this safe level, yeah? Let me just check the question. Yeah, find the earliest time. Yeah, so that's fine. We can just find the first time after it passes the equilibrium. Well, our equation was x equals minus x naught cos omega t, right? But then above the equilibrium by, it is 8.5 above the ground, right? So it's just 1.5 above the equilibrium. So we put this as a positive 1.5, yeah? And then it should be an obtuse angle for the cos, because cos is negative, then you get a positive value here. So this is minus 3 cos omega t, yeah? So that's just minus 1/2 equals cos omega t. I'm just going to solve for the angle first. Again, I mean, if you use the pure math knowledge here, you solve for the negative cos, you should get an obtuse angle. So if you just do a calculator there, arc cos minus 1 over 2, you're going to get, I believe, 2 pi over 3, yeah? So 2 pi over 3 here, yeah? I mean, let me check that, right? So radian arc cos minus 0.5, yeah, 2 pi over 3, yeah? And then that will be equal to omega t. So omega is 3 pi over 19 and times t. So t, note that t is in hours, right? Still, we don't change the unit here. Pi cancel, that's good. So we get 38, yeah, over 9 to be t. So t equals, what is that? So if we do t here in hours, 38 over 9, yeah, that's going to be 4.22 dot dot dot. If you multiply this guy by 60, that's going to be in minutes, yeah? Minutes, right? So that's like what, 4 hours. 4 hours is 240 minutes. 4 hours and 13 minutes, yeah? So that's 4 hours and 13 minutes. Yeah, if you round that, because the 0.33 is like rounded down, rounded off. So the time then is, if you add 4 hours to 12 o'clock, you get 16, yeah, and then 16:13. That's the time. It is, for the first time, safe to enter the harbor. And we already given in nearest minute, so we are good. Yeah? That's it. Question 5. A uniform rigid, let me do this page. A uniform rigid solid circular cone C has a radius r and a height 4r. A, show using algebraic integration that the distance of the center of mass of C from its vertex is 3r. Okay, uniform circular cone. Yeah, uniform circular, solid circular cone. All right. Okay, so what do we do? Okay, we have, let's say we have an x and a y here, yeah? And that's x, that's y maybe. So I'm gonna do, so for a solid circular cone, we're just gonna have to do solid of revolution of this graph here and this area here, yeah? And the radius is r, so that's gonna be r here on the y-axis, and the height is 4r. So this is 4r here, yeah? Okay, so if we do the solid of revolution, you're gonna get a cone, right? And we want to find the center of mass from the vertex here, note, from this. We don't forget because we're gonna do from the origin, but then we're gonna subtract that from 4r, right? Okay, so the formula, right? We're gonna find the x bar here, so the x bar will be, I have to recall this, so it's pi. So let me get the volume first. The volume is just from P4 integration, so it's pi integral y squared dx, right? That's usually the solid, so that's like the volume. If you, or the mass, right? So volume or mass, because this is uniform. So you have to multiply by lambda somewhere. But lambda will cancel because on the top part you also have y squared, which is the, you take that as the radius and you time x. So there will actually be lambda here and lambda here, but they cancel because this is uniform, right? If lambda depended on the distance from the center, then that's another story. But it doesn't here, so that's fine. We're good. So pi cancel there, and then we have to get this equation. So this is y equals mx plus c. Okay, the most basic function there. And then this is just what? The gradient is a negative value, so that's negative r over 4r, right? So that's negative 1 over 4, yeah? Yeah, x plus c, so c should be r, right? Because the y-intercept is r. So that's the equation there. So we're going to integrate that, 1 over 4x plus r squared and times x dx divided by integral, the same thing here. Yeah. Seems like the top part we need to do by parts maybe. Maybe by parts is better. Yeah. So I'm going to split there. So for this one, we're going to do by parts. So I'm going to make that u and this dv, right? So that means that will be equal to uv, right? So it's u. If you integrate this, we can use reverse chain rule. So that's going to be minus 1 over 4. I mean, I'm thinking, should we just expand? Might be easier. Or should we keep along with this? Let's see. Maybe I'm going to expand. Okay, let's expand, you know. So, okay, so that's integral, that's top, integral 1 over 16 x squared plus 2 times the first times the second, so that's minus 2 times the first is a half, so it's a half xr, right? Plus r squared times x dx. So if we expand that all in, I get what? X squared, I get x cubed here, x squared here, x here, yeah, and dx, like that. Okay? Oh, this is r squared, sorry. Yeah, just checking. Everything is good. Okay, then we integrate that, we get, do we need to show, yeah, we're gonna do the bounds later maybe. Yeah, we just get the integral first, so that's x to the 4 over 64 minus x to the r x to the 3 over 6, right? plus r to the 2 over 2 x squared. Then that's it. That's the top bit. And then the bottom bit is just easy, yeah. So it's just integral that, and we can use the reverse chain rule. So it's going to be just 1/2 x plus r to the power of 3 over 3. And then here we have to also divide by the reverse chain rule inside, which is minus 1/2. Okay, so that is just what? Minus 2 over 3 minus 1/2 x plus r to the power of 3. Yeah, so if we bring those things to our thing here and then apply the bound, so it's going to be from 0 to 4r. Okay, so x over 64 to the 4 minus r x to the 3 over 6 plus r to the 2 x squared over 2. The bounds are separate, right? So you apply separately, 0 to 4r, all divided by, this is also minus 2 over 3, and then that, 0 to 4r. Okay, so that's the work there. Okay, see if I copy everything correctly, right? Okay, so we're gonna go from 0 to 4r. Okay, that's some work there. I mean, if we look at the lower limit here, subbing all in, we get 0. That's convenient, right? Yeah. So if we sub just 4r into the expression there for the top bit, we get 60. Wait, 4 to the power of 4, what's that? It's 2 to the 8. So it's 4 to the power of 4 is 16 to the power of 2, right? So that's 256. R to the 4 over 64 minus, that's 64 r to the 4, right? Because it's power over 6 plus, that's 4 r to the 4 over 2, yeah. And then the lower limit disappear because it's 0, and then the bottom bit here we have you sub 4r in, you get minus 2r on the first bit, and then plus r, so you get minus r here to the power of 3, yeah. And then you sub 0 in, you have r to the power of 3, right? And then all that multiplied by minus 2/3. Okay, so the top bit is what? I'm just gonna factorize r to the 4 out and just do the fraction there, guys, yeah. So that's fraction 256 over 64, wait, what? Minus 64 over 6, yeah, and then plus 4 over 2 is 2. Okay, just gonna write minus 14 over 3 r to the 4, and then the bottom bit is just minus 1 is minus 2, so 4 over 3, right? 4 over 3. I get a negative number here. Okay, let's see what went wrong. Yeah, we should be expecting something of a nice number. Okay, seems like I don't get that. Hang on. Okay, I still have time, I guess. Its vertex is 3r. Okay. So we expect like r, actually. We expect r to be the answer from this integration. So let me see. This is 16 x squared half xr, then r squared x, yeah, everything multiplies, so that's over 4, that's over 3 and 6, it's over 2 here. And then did I do this right? Oh, hang on, where did I get that half? Oh yeah, it should be a half, sorry, yeah. What about this one? 3 over 3, and then divide by that, which should be minus here, and also 0 to 4r, so it's the same bounds, right? Okay. 3/2. So the top bit is that guy. So we have 4r in. Yeah, I think that's fine. 4 in here, 64/6 to the 4 as well. That is a plus in it. Yeah, it should be. Oh, that is 16. Gotcha. Okay. Here we go. Okay, so I gotta start this over again, right? So, oh, not over. It's just change that to 8, right? Yeah. Ooh, so yeah, that's that works now, right? So that is 4/3 instead, right? And it's a positive, so we get positive and positive. So that is just r, as expected. So that means the distance from center of mass from its vertex. So therefore, distance of center of mass cm from vertex is 3r. Yeah, because we got this to be r, right? So we can just do 4r minus r equals 3r, and that's the answer. All right. Whew, that was some hard work there, although just 4 marks, but yeah, not to be underestimated. Now we got that cone. A uniform solid S shown below in figure 3 is formed by removing from C, yeah, a uniform solid right circular cylinder of height r, radius 1/2 r, where the center of one end of the cylinder coincides with the center of the plane face of C. Yeah, okay. And the axis of cylinder coincides with the axis of C. All right. So it's just saying that the base of the cylinder here is just on the base of the cone, basically. B, show that the distance of the center of mass of S from the vertex of C is that. Now we use composite body. Yeah, the concept of composite body. Maybe we should do a table. Maybe easier. Okay, so here I'm going to write the cone, yeah, and the cylinder, right? So we're going to go from, the vertex. Distance from vertex, yeah? So the distance from the vertex of the cone is, again, 3r. We have proven that, right? 3r. Yeah? Wait. That should be on the row here. Yeah, x from vertex. Okay. And then, now this is a uniform cylinder, right? We're moving a uniform solid right circular cylinder. So the center of mass of the cylinder should be halfway. Yeah, so it's just half r here. So that's going to be what? From the vertex here is 3r and another half r. So that's 3.5r, which is 7/2r, right? So 7/2r from the vertex, right? And then, yeah, we just find volume here because volume will matter here, not the area, just like we did in M2. So the volume of the cone should be 1/3 pi r squared h is 4r. The volume of the cylinder, that's an ugly cylinder, right, is pi r squared h. Well, r is just 1/2 r. I got to be careful there. So that's 1/2 r, and then h is r, right? So the distance of center of mass, x bar of S, is just, we do composite here because that is removing, so we're going to use subtraction. So it's just sigma, xv divided by sigma v, right? So use subtraction there. X is just 3r times the volume. So I'm just doing everything here, and it's going to be 4. So that's 4/3 pi r cubed. Minus, right? Because it's a subtraction there. Then minus what? 7/2, not 7 over 2r times, so that's r squared over 4, so pi over 4 times r cubed, right? Yeah. Or divided by, the volume should also subtract, so it's a third, is again is 4 over 3 pi r cubed, right? Yeah, I'm just checking. Minus pi over 4 r cubed. Yeah, hopefully that should work. Okay, so let's simplify that. Of course, pi will cancel, r will cancel. Wait, r won't cancel. Oh, r will cancel. Cancel, so that we have just one r left, right? So the 3 cancel there, so I have 4 on top here. Minus, right? I'm just gonna look at the number there. And this will be just what? 7 over 8. Yeah, and this is divided by, because the pi's go away, 3 of the r's go away. I'm gonna have an r here, right? And then the bottom bit will just be 3 over 4 minus 1 over 4, right? Yeah. So that's what? 32 minus 7 over 8 divided by, what's that? 16 minus 1 over 12, r. Yeah. 32 minus 7 is 25. 25 over 8 times 12 over 15. So 5 cancel, 5 cancel, 4 cancel, 4 cancel there. Oops. That doesn't look right. Hang on. What went wrong? Okay. 32 minus 7 is 25. Yeah, 25 over 8. 16 minus... Just use calculator maybe. 25 over 8. 15 over 12. That's 5 over 2. That's not right. It's too simplified here. Something is wrong with my calculation. Let me double check everything. Yeah. So we have proven that the center of mass of the cone is that, and then we remove. So subtraction is fine. 1 over 3 pi r squared h. Yeah, that should be the right formula for a cone. And then for the cylinder is pi r squared h. Okay, pi r squared, so that's r squared over 4. That's pi over 4 r cubed. Yeah. 4. And that's 7 over 2. Right, so, is there anything about the density that I'm missing here? No. 4 pi r to the 4 minus 7 over 8 over 4 over 3 minus 1 over 4. Not sure what went wrong here, guys. I don't see it yet. Okay. Let me just think a bit, yeah? I'm just going to check one last time and to see what went wrong here. If I don't see it, I'm going to skip this one to do part C maybe. And then let's see how that goes. We are removing, so yeah, so that should be right. Hang on, let me check some sanity check here first. That is less than 3r. Yeah, it should be a little less than 3r. The radius of the cylinder is half r, so that's right. That's pi over 4. Yeah. What's wrong? You know, I'm just gonna plug everything to the calculator. Maybe I did somewhere, you know, I might make some stupid mistake somewhere and I didn't see. So I'm just gonna use a calculator for everything here. Oh! Right, yeah, okay. It must have been my stupidity in mental math or something. Yeah, okay. You never know. And I couldn't still see it, guys. If you saw it, just maybe comment, you know. There you go. All right. Oh, I almost died there. Okay. Part C. A rough plane is inclined at an angle alpha to the horizontal. Okay. Solid S rests in equilibrium with its plane face in contact like this, maybe. So that's the cone. Yeah. Given that S is on the point of toppling, so when it's on the point of toppling, right, you should know that, so given that the center of mass is here, yeah, it's just going to be vertically down like that on the point of toppling, okay? And this is alpha, right? Okay. Find the exact value of tan alpha, right? So if that is alpha, right, and there is some similar triangle here that we can use, so that is also alpha, I think, because these two would be the same angle, right? Yeah, so if that's alpha, that's also alpha. Now, we already know that the center of mass of the new face, the new shape S here, is 75 over 26r from that. So this distance here, let's say x, right? So x is going to be, you just do 4r minus 75 over 26r. What is that? I'm not going to mental math now. 4 minus 20, what's that again? 25 over 26. 76 over 25. Oh, okay. I'm going to kill myself there. 24 over 25r, right? Wait, what? Oh, no. Something wrong with me today, guys. It's, yeah. Yeah, it should be that, right? Okay. You never know. Silly mistakes can come anytime. Okay. 29 over 26. Yeah? R. All right. Here we go. Okay, so that's the x distance. Now, we also know that this is just the radius of the cone thing, which is r. So there you go, tan alpha. So tan alpha is just, if you do the Pythagoras, sorry, not Pythagoras, the trick there, the SOHCAHTOA, is just r over x, right? Which is, yeah, r over 29 over 26r. So tan alpha would just be 26 over 29. Exact value. That's it. That's not too bad, right? On the point of toppling. So you just have to know that the center of mass will be vertically aligned with the point of toppling, which is this point. It's going to tilt down there because there is a net moment. So that's why it topples. Okay. Number 6, we're at 1 hour. How many questions? 7, I hope. Yes. Okay. We are cool. We are cool. Number 6, circular, vertical, circular motion. A fixed solid sphere has center O and radius r. A particle P of mass m is held at rest on the smooth surface of sphere at A. The highest point of the sphere, the particle P, is then projected horizontally from A with the speed u. Good. And move on the surface of sphere. At the instant when P reaches the point B, the sphere where angle is theta, P is moving with the speed V, as shown in figure 4. At this instant, P loses contact. So it's saying that R is 0 there. Yeah? So part A shows that cos theta is that. All right. Okay, let me think a bit. So it loses contact at point B. So we're just going to do point B here. So that's point A. That's point B there. Speed V down here, yeah? Okay. And this is theta. All right. So if we do the force diagram, yeah, we have, of course, mg down here, yeah, as mg, yeah, mass m, mg. And then r, yeah, r is pointing that way. That's r, because it's just normal to the, you know, surface there, like that. And then this is circular motion, right? So that means you need to resolve the force into the center. Okay, that means this is also theta. Okay, so if we do force along the center there, towards the center, that direction, so we have mg cos theta, right, minus r equals mv squared over r is little r. The big R is the normal reaction, yeah? And we know that at this point, R is 0, right? So it's just mg cos theta equals mv squared over r. So we're going to leave it at this now. We know that we are asked to find cos theta, right? So it's v squared over rg. Well, by the looks of the expression there, we need to show it doesn't have a v. So we need to get some idea about the v. And the v is kinetic energy. V squared here is from kinetic energy, right? So because at point P, you have some kinetic energy. So we use energy conservation here. Conservation of energy, right? So from A to B. So from A, let's say from, okay, you can consider conservation energy as the energy loss is going to be equal to the energy gain. Yeah? So here the energy loss is the GPE. You lose GPE there because you're moving down. So GPE loss is equal to KE gain, right? Yeah? And there's no friction here because it's smooth, all right? So GPE loss is just working out that little distance here. This little distance. Well, we can just draw a right angle triangle here, right? So, of course, this is R, this is also R, right? So this is a big distance, R. We're going to subtract this distance from this distance to get this little distance. Yeah, you follow? So the big distance is just big R, the radius of the sphere, minus, well, this little distance is just R cos theta, right? Like that. So that is the change in height, which is the GPE loss. So we do mg r minus r cos theta here equals, yeah, KE gain. So that's half m v squared minus half m u, you subtract the v squared and the v squared. So the first one is just u squared and the other one is v squared. Well, you are gaining, right? So hang on, v squared should be more than u squared, right? Because u squared is the initial speed. So it seems like I need to make v squared the subject to get the expression of v squared so that I can sub here, right? Yeah. So m cancel, all right? So we can get r. So this is gr 1 minus cos theta equals half v squared minus u squared. Okay, so that's 2gr 1 minus cos theta. Hang on. We get 2 cos here, hang on. Equals v squared minus u squared. Okay. So v squared equals, wait, or do I get, u squared plus 2gr 1 minus cos theta, like that. If I plug that in, yeah, okay, I need to plug that in so that I simplify the cos. So cos theta equals u squared plus 2g, I'm going to expand that as well, 2gr minus 2gr cos theta, I should have known, divided by gr, okay? So you can see that if we simplify on that on either side, we have gr cos theta equals u squared plus 2gr minus 2gr cos theta. We need to make cos theta the subject here, so we merge the terms. So if you move that to the other side, you get 3gr cos theta equals u squared plus 2gr, right? Let me just shrink the whole thing down, because I think keeping it on the same page, you can see it better. Okay. So here we can make cos theta the subject, and I hope that would be as required, right? Yep, it is. There you go. That's part A. Yeah. Ooh, 7 marks. Okay. In the subsequent motion, the particle P crosses the horizontal through O. Particle P crosses through the horizontal through O. Wait, what? The horizontal through O at point C. Okay. It means that just passing point C. All right. Shown in figure 4. At the instant P, as the instant P passes through point C, P is moving at an angle alpha to the horizontal. Right. So it's doing that. So let's say that's the horizontal there. This is the circle, right? That's O. So it's moving like that. Passes through C, and then the velocity is like that. And this is alpha. Yeah, just quick sketch there. Given that u squared is that, okay, we can do cos theta now. Find the exact value of tan alpha. Okay. So because this is out of the contact already, so when it's out of the contact at B there, and this is again at A, we have initial speed when it's out of the contact as V, right? So here is projectile, yeah? Let me just delete the sphere now. We know that it's projectile now, yeah? Just like that, yeah? So this angle right here, right, is not to be the same as this angle right here. So don't fool yourself. I mean, I might fool myself here, but hang on, let me just, yeah. So V might be more like this. Like that. Because by the time you're falling down here, you have more vertical speed. So that will make it more like steep down, yeah? So it's like, at this point, it might be something like this. At this point, might be something like this. And down here might be something like this, yeah? Because you have more and more downward vertical speed. So it's going to be more to the, you know, it will be more to the downward vertical there. Okay. So let's make it a little less deceiving there. So this is V, okay? Now, what is the angle there again? So that was the center. This was theta. So theta here is also the same as the angle to the horizontal here, theta, right? Yeah, we can go back here to, so if we draw a perpendicular line here, that should be the, hang on, this is V, right? So yeah, so this is 90 minus theta, so this is also theta, right? Just do geometry there, you will know that the depression angle of V there would be theta as well. Okay, so we do SUVAT, projectile, okay? Let's see. So we want the, the alpha here. Right, so we get some idea about the distance fallen here, which should be r cos theta, right? So distance fallen. So let's do vertical. Yeah. We're just gonna do downward as positive, right? If you don't mind, because it's going down and G is down, right? So S is going to be r cos theta. That's the distance fallen from point B to the horizontal vertically, yeah. And U is just the V, right? The V there, V sine theta, yeah. And V, which is the final speed, not to be the same as a V there, is what we don't know. We don't care actually. Well, we might care. Hang on. We might care. We do care because we want the angle at which it makes with the horizontal. Yeah, we do care. We want to find this. And A is just G. And yeah, this one we don't know. We don't care. Okay, so the equation would be V squared equals U squared plus 2AS. So V squared is what we want to find. U squared is V squared sine squared theta, right? And plus 2GS is R cos theta. Okay, so that is the V squared, the VY squared here, yeah? VY squared. I'm going to leave it as VY squared. Let's see, yeah? Because I feel like it's probably useful that way. Now, we are given that the U squared is that. What is the V squared again? We get V squared here. Hang on. V was what? Okay, V was cos theta Rg, right? V squared equals cos theta Rg here, yeah? So that's V squared, right? Yeah. Cos theta Rg, isn't it? Yeah. Sine squared theta plus 2gr cos theta. That's a lot of trick terms there. Can we simplify this? Oh, we know that cos theta is that. So hang on. So from the thing that is given there as U squared, we can put it in here. So cos theta is 2gr. U squared is given to be 2gr over 5, right? So we plug that in. And we use this. So it's going to be calculator. 2 plus, I'm going to cancel all the grs, yeah? 2 over 5 over 3. So that's simple, 4 over 5. Okay. So again, using the triangle trick there, I'm going to get sine as 3 over 5, yeah? So Vy squared here is then 4 over 5 Rg times 3 over 5 squared is 9 over 25 plus 2gr times 4 over 5. Just subbing in everything. Okay. Let's see. So we have, what is that? 4 over 5 times 9 over 25, right? Yeah. And then plus, what's that? 8 over 5, right? Ooh. Is that coincident or something? I saw that number earlier on. Yeah. 76 over 25. Okay. GR. Okay. So we know that at this point, the V squared here is that. Yeah. So that's Vy. Well, now Vx doesn't change, right? So Vx will be, so Vx is, at that point, is the same as V cos theta, which is, so if we do Vx squared, right? Wait, why am I doing this? I want to find tan, so I should, well, yeah, let me get Vy, yeah? So that's going to be square root that, right? 76 over 25 gr. So Vx is just V cos theta. Cos theta is already 4 over 5. And the V, what is the V? V is root cos theta Rg. Right? So that is cos theta is 4 over 5 again. So I'm just going to put everything in the root. Okay? Yeah. Cos theta. Is that right? Yep. I think that's fine. So cos theta is 4 over 5. So that's going to be, I think, yeah, if we put 4 over 5 inside and times the 4 over 5 for the cos there, we're going to get 64 over 125 Rg, right? Just going to tidy everything here. We are almost done. Oh no. So yeah, so tan alpha, right? So let's see, tan alpha, right? So alpha is the angle with the horizontal, which is this guy right here. So that's going to be Vy over Vx, yeah? Still. So that's square root 76 over 25 divided by 64 over 125, and GR cancels, right? So I'm going to use a calculator. It's probably not my mental math day, I guess. Fraction 76 over 25 down here, 64 over 125. Okay, so that's just root 95 over 4. Exact. Oh yeah, that's fine. That's done then. There you go. Hurry up, hurry up. Number 7. 15 minutes left. Okay. Can you see the? Yeah, you should be able to. Part A. A particle of mass m is attached to one end of the light elastic string of natural length L, modulo of elasticity 2 mg. So lambda is 2 mg there. Okay, the other end of the string is attached to a fixed point A on a smooth table. Okay, A on a smooth table. The particle P is at rest at point B, where AB is now L. So this is at natural length. Doesn't have any tension or stretching. At t equals 0, P is projected along the table with the speed u in the direction AB. So it's going to go like that. Yeah? In the direction AB. So just go from A to B. Yeah. Elastic string has not gone slack. Okay. And BP equals X. P is projected along the string. Okay, so it's saying that the particle will move up here. Yeah. X here. Yeah. Okay. Speed of P is V. So here is V. Show that. Okay, so we use energy conservation again. Conservation of energy. So at B you have kinetic energy. You are transferring that to elastic potential. And you still do have elastic potential as well as kinetic there. Okay, so at point B you only have kinetic. So kinetic at point B will be equal to kinetic at point, I'm just going to call this point P, all right? Plus some EPE at point P, yeah? So kinetic energy have mu squared, because that's the initial speed, equals the remaining kinetic energy, which is V now, half mv squared, plus EPE at point P. Well, you have stretched the length by x. X is the extension, so we do half. Well, from what I know, right, k, which is the the spring constant, if you like, would be lambda over natural length. Yeah. So that's 2 mg over L. So the in energy here is half k, which is that, and x squared, right? Half kx squared. Well, you guys probably do physics as well, if you are up to this point. We cancel the half, we cancel the m, we get u squared equals v squared plus, cancel the half, so we get 2 mg left. Oh, m is already cancelled. We get 2g over L x squared. Is that right? Yeah, so we rearrange, so v squared equals big U squared minus 2g over L x squared. Yeah, that's done, as shown, as required. Part B. By differentiating this equation with respect to x, prove that before the elastic string goes slack, P moves with simple harmonic motion with period of that. Okay, so to prove simple harmonic motion, right, we require that the second derivative of x is going to be equal minus omega squared x. That's what we want. So if we differentiate that twice, okay, if we do implicit differentiation, right? Yeah, differentiating v respect to x. So we get 2v dv by dx, right? equals u squared. Well, that should go to 0 because u is a constant, right? So minus here, 2 brought down, so we get 4g over L and then x here. Okay? Well, probably have to differentiate dv by dx again. Is that any use? Well, yeah. Okay. This is acceleration, so we need to get acceleration in the picture. And we know that acceleration over v is dv by dx, isn't it? Yeah, I used that earlier, if you remember. So dv by dx, we can change that to a over v. Can we not? Yeah? Okay, so the v cancel there. That means 2a equals minus 4g over lx. That means that's x double dot, right? Which is second derivative of displacement. That's going to be minus 2g over lx. Yeah? So we now have proven that because g, l are constant, so minus 2g over l is constant. Therefore, x double dot is proportional to minus x. Therefore, simple harmonic motion. Yeah? And we need to find the period as well. So we already know that that thing will be omega squared. Right? So omega squared will be 2g over L. But omega squared is just 2 pi over period squared. Right? So that means I'm going to be quite quick here. I'm losing time. So 4 pi squared over t squared equals 2g over L. Right? So I think we can prove now that period is just that. So if I do the cancellation there, t equals square root 2 pi squared over g times L here. Yeah, I think that's what it wants. So pi square root 2L over g as required. That's the period. Okay, C, the last one, guys. Given that u is gl over 2, find in terms of L and g the exact total time from the instance it is projected from B. It is projected from B. So in terms of L and G, the exact total time is projected from B, yeah. That it takes P to travel, total distance of that. Right. Okay. Okay, so interesting. How about we know that v is dx by dt, because that's the only way we get time in the picture there. This is 6 marks. See if I can make it. Okay. Ooh. Aha. So we already got the first derivative there. This is just, the previous equation we got earlier. Equals minus 4g over lx here, right? If we multiply both sides by dx by dt, v here is the dx by dt, right? So 2 dx by dt times dv by dx equals minus 4g over lx. So the dx here will cancel. We get v in terms of t, which is what we want. We want to find time, right? Total distance, probably not. Hang on. What am I doing? Total distance. We should have, we should have I think we can use that, right? The acceleration there is dv by dt. So, hang on. Wait, this is simple harmonic motion. So, I shouldn't be thinking too much, should I? I'm losing time, guys. Hang on. Probably spent too long checking my mental math error back then. Yeah, okay, let's start from here. So x is then x naught, let's say sine omega t, yeah? We already know omega, that's fine, but x naught we don't quite know. Total distance, that's tricky, that's very tricky. Okay, I think I'm not gonna make it for this one. But then if I run out of time, I'll make sure I explain this properly. Yeah. Okay. So let's find v squared from there first. So that's gonna be just plugging in that. So gl over 2 minus 2gx squared over l. And then so v is dx by dt, right? That's just dx by dt squared. That's not gonna help. I don't think so. Okay. So it's gonna go back, right? It's gonna go back about the equilibrium. So equilibrium is when the B. Aha, hang on. So projected from B. So equilibrium is at B. And then it's gonna go there. Okay, I think I got it. So the amplitude will be when the kinetic energy is out. So amplitude is when V is 0. So we put V is 0 to find the amplitude. So 0 equals U squared, which is GL over 2 minus 2GX squared over L. That will give us the amplitude, guys. Let me just 3 minutes. Okay, so X naught here is equal to, we cut the G, it's going to be L over 2 here times L divided by 2 square root. So that will be L over 2, right? Yeah, it will be L over 2. So L over 2. So L over 2 is just halfway. So it's going to go back by a quarter. So this is at B. This is at the, amplitude X naught. Is going to go back by 3 over 4. So it's going to be halfway here. So that's halfway. So if we assume that x is x naught sine omega t, then if we do x here as x naught over 2 equals x naught sine omega t, right? So if we arc sine a half, we get what's that, pi over 6 equals omega t. So t is just going to be pi over 6 times 1 over omega. Omega was what again? We got omega to be root 2g over L. And root L here. Alright, that's ugly. Okay, so that's the t. And then we have to add this time. Wait, hang on. This is to that t. So we got to do half period minus this to get the time from this to this. So the time from this to this is half the period. So it's going to be half the period plus half the period minus that pi over 6 root L over root 2g. So the period, is pi, that. So I just do pi over 2 root 2L over g here. And then, wait, hang on. Let's simplify this. This is just 1t, right? So that's just 1t, which is pi root 2L over g, but then minus pi over 6 root 2L over g. So that's just what? 5 over 6 pi root 2L over g. That's my answer there, guys. Just last minutes. I'm not sure if that's correct, but 5 over 6 pi root 2L over g is my last minute answer. Just going to stop the timer and mark the paper. Okay, guys, here's the mark scheme for M3 June 2024. Right, let's see how well I did. Actually, I have no idea. Okay, let's see. Okay, so that one is as required, so I'm gonna mark myself correct there, and yeah, k is 4/3, so that's fine. Number 2, yeah, mga over d, that's fine. 2b, yep, that's still great. So far so good. A, yeah, as required because we proved it. B, not sure now. Yeah, okay, it's still correct. So far, still so good. All right, so for 1.1, 1.05, yeah, correct. B, yep, correct. 1613. Number 5, that should be fine. I proved it. And that is 75 over 26R. Yep, nailed it, guys. Nailed it. So far, so good. No mistakes yet. A, I did prove it, didn't I? You guys witnessed, yeah? Okay. B, root, wait, what? Wait, did I saw something wrong there? It's just swapping the numbers. Oh no. Okay. First mistake. So cos is 4/5. Yeah, I got B1 there. Yeah, this one I got. V squared equals 2RG there. Yeah, I think I got that one too, because I used it somewhere. I remember. Didn't I? It's M1. So V squared. Where did I use V squared? Yeah, I think I used it here, right? Yeah. So that's M1 there. And then horizontal at C. Where I get, yeah, this one. Okay. And then vertical. Vertical at C. I have no idea how they get 236 RG there. Okay, so probably I don't get that speed at C. And then they got that, so no idea now after this. Probably wrong here, guys. Yeah. Okay. Yeah, so I got a different VY, right? Yeah, different VY. Yeah, but the same Vx, right? Yeah, I got the same Vx, but different Vy. Okay. Vy is V sine, yeah, plus 2RG cos. Yeah, I got this method, right? Because I plug V sine squared there. Yeah. Okay. Yeah, I think I plugged that in. So this line is wrong. So I got this wrong somehow. Is that mental math error or not? Okay, let me check that line. The Vy squared line here, yeah? So that's 4/5 times 1/125. No, 25 plus 8/5. Huh? What? Huh. That's way out of still. Oh, that's a sine. Wait. Sine squared V sine V. Okay. So V is root. Hang on. Okay. So I think it's something to do with this term. Yeah, definitely. That term is wrong. So yeah, V sine theta squared there, where V is just the speed. V was root 4RG. I think I used that, didn't I? Yeah, so V squared here is 4/5RG, right? Yeah. But then, yeah, I plug here V squared 4/5RG. Then I multiply with the sine squared, but sine was 3/5, so that's 9/25. So sine was 3/5 squared, that's 9/25, no? How come? Let me check calculator again. Oh, 9. Forgot 9 there. Yeah, there you go. All right. Silly mistake here, guys. Okay, but I got the method mark. And then I think speed. Why do they find speed? They don't need to, right? I mean, they could have done Vy over Vx. Yeah, vertical over horizontal. Yeah, so if they did, yeah, okay, so it's a follow through here, I think. Probably I lost 1 mark here, guys, because there's a follow through. I got it wrong here and then wrong here. This one is a method mark. Because there's no accuracy here required, so I lost 1 here, the final one. All right? Okay. The last one. Should be fine. I proved it here. And then B, let's see if the last one I'm correct. Yeah, B. Wait, where's B? Wait, there is a C? Wait, hang on. This is a C. Yeah, I forgot to add that. Okay. So this, where's the B? Hang on. Where? Let me check the question again. Yeah, I already proved that. Okay, no, this is a B. Yeah, this whole thing. This is a C, sorry. Yeah, I proved it. C. Oh, guys. Wait, what? 2L over G? Oh no, I copied it wrong. This is L over 2G, but I copied 2L over G. Okay, guys. Yeah, alright. I almost got the marks here. If I didn't make that stupid last mistake there. But yeah, I think everything you can follow here. Like the amplitude here, they use a little a there. This is L over 2, yeah. And period here, I think I got it here, yeah. This is the right period, right? Pi over 3. Wait, hang on. No, that's not right. Uh-oh. Oh, yeah, because when I divide this by omega, what was omega again? Omega was root 2G over L, right? So, well, that's right. Hang on. Pi over 6. I think this should be right because they probably did differently with the simple harmonic motion there, but hang on, let me check. So that's 1 period. So I did half period here and add with another that, where the time taken from the most right to that is just going to be, actually we can do, hang on. Oh, this is not half a period, this is a quarter of a period, isn't it? Yeah, and this, oh guys, right. So it should have been a quarter and a quarter here, so that should be half the period, right? Yeah. Right, so yeah, hang on, let me just use red pen here. So that should be a quarter, and that's going to be half minus pi over 6. So that would be, yeah, wait, no, hang on. Pi over 3. Period is not pi over 6. Oh, that's little t, sorry. I think they use, yeah, a slightly different method. All right. I think I'm not going to give myself marks here. Time from x equals a to x equals a quarter L. Yeah. A quarter L. Yeah. It's given by that. Yeah. Okay, so this is, they use, yeah, okay, so they use the formula to calculate the time directly from this point to this point, right? So they get that. I didn't do that. I just did from equilibrium to that point instead. Yeah, which should have been fine as long as I get the right, yeah, I think this would have been fine if I use it correctly. Yeah, because this is the equilibrium position, right? And that is the amplitude. So I could have said an equation. I did. I said an equation x equals x naught sine omega t, where assuming that it starts from here. So if you start from here and you go by that distance, you're going to set this as x naught over 2. So I solve that and I get the period, the little time to be that. But then you got to go this by t over 4. Or actually, you can go this back to this. This is going to be a half period. And then you subtract by that t. So let me try that, yeah? So it's a half minus that little t. Yeah, the time taken. So half a period. So the period was root 2L over G, right? So root 2L over G and divide by 2. So that's 1 over 2 there. And then minus the little time, this guy right here, right? And that is minus pi over, wait, hang on. Period has also pi here, sorry. Pi over 6, root L over 2G, yeah? Wait, hang on. Root 2L over G, that's 2L over G. Omega was 2G over L, root 2G over L. Yeah, that's right, okay. So this is then what? That's a little complicated. I should bring the root out. So we're going to simplify this, yeah? This thing to get the answer. So that would have been complicated. We keep it as L over 2G, right? So L over 2G. So if I take the root out, probably not a good idea there. It doesn't look simplified. But if I throw the 2 inside, yeah, I get L over 2G, yeah. Because if you throw the 2 inside, you get 1 over 4 there, multiplying with the 2L over G. Yeah, so that's, yeah, I think we get the answer. So we get 5 pi over 6 and root L over 2G. Yeah, we would have got the answer here. So this is usable. So I'm going to mark myself there, up. And if I didn't make this final mistake here about the, yeah, so I think I lost 2 marks because I did this line wrong. It should have been just, should have been just, yeah, should have been just this. So you guys, when you see my work, you just look at this, yeah, for this question. And I lost 2 marks there. Okay. All right, just not gonna, yeah. So I lost 2 marks, so I lost in total 3 marks, right? Yeah, 1 there. And then that was it. I think this paper is not easy though. I mean, again, I haven't done M3 for a while, so from yesterday to today, I spent like in total an hour to revise the summary contents and everything. I used to teach it 2 years ago, and then after that, I didn't do any M3 at all. And then, yeah. So, yeah, so totally, actually it's not easy. Every question here can be tricky, right? So it tests you well on the math skills and calculus. Almost all of them involves calculus. But yeah, if you guys have any question, you give me a comment. But that was it. I hope that was useful. So I got 72 out of 75 here. Not bad. So not bad. And I'll see you in the next one. Bye.